Yeah. So the keyword is the adiabatic process, for which we know PV gamma is a constant. But in this case, we want to relate T and P, so we'll use ideal gas law to get rid of volume. And then we take a derivative on this using product rule. So if we multiply P to the gamma and divide by T to the gamma, if we do that, this happens. And then we divide by P. That is the relationship, right? Yeah. And then express the pressure difference dP in terms of dz, the change in height. In the air, there must be a pressure build up because the weight of the air is balanced by pressure. So if we imagine we have a column of air, this is at a height z. The pressure here is Pz. The pressure here is Pz plus dz. And this air has certain temperature, density, which all depend on height. And let's also imagine the cross-sectional area is A, right? So the stability of the air, because the slab of air rises slowly, that implies the air is very stable, equilibrium. Therefore, PZA minus PZ plus DZA must equal rho A DZG. And the left hand side is simply negative dp a equals well, let's get rid of a at this point, the cross-sectional area, rho g dz. Okay, and on the other hand, we know we still have ideal gas. PV equals nRT. So P is equal to N over V RT. And then if we multiply the molar mass of nitrogen, 28, okay? This is a standard relationship. Density can be, you can get density out of the ideal gas law. So this becomes rho RT over the molar mass of nitrogen, which is 28 grams per mole. Therefore, density is PM over RT. So that's what we will put back into the pressure differential equation. Negative dP equals PM RT G dz. So far, so good? Mhm. So how do we find the temperature at the very top? Okay. Okay. Now we have both relationships. Mm. That's exactly right. Yeah. So now we copy that equation down here. So we solve dP. dP is negative gamma over 1 minus gamma P over T dt. Okay. We don't really want P, so we use the density formula again. we could use the density formula again, problem. But let's see, maybe P will cancel out. So we can then just plug this into the second one, or the P will cancel out. So T will also cancel out. So it's really a linear relationship. Okay, so we conclude that's equal to MR GdZ. Yeah, that's good because 1 minus gamma is a negative number. So as Z increases, T will decrease. That's 28 grams per mole for nitrogen, right? Molar mass. So T at Z will be T 0, okay, plus big M G over R, 1 minus gamma over gamma, which is a negative number, times C. So we have the temperature at the bottom, which is 30 degrees. We have 28 grams per mole. It would be necessary to convert this into kilograms per mole. 10 for G, 8.314 for R. Gamma is 7 over 5. And height is 1000. Yeah. Mm-hmm. Mm-hmm. Mm. It shouldn't matter because that's a difference term, right? That is a delta. That's a delta. It's not absolute temperature. The second term. Um, I mean, we can try this quickly. Let me put this into Wolfram alpha. So I have 1000. Yeah, that's the result. That's the correct result. Sounds good? Okay, so let's look at the next one. This one is surface tension. I believe these questions they all turned into bigger IPHO or APHO questions. I've seen the bigger ones, more complex version of them. This question also has a very useful, this there's a very useful idea coming out of this question, that is, for all transport process, flow of water, flow of current, flow of wells, flow of knowledge, flow of anything, you can use Ohm's law to model that. And in fact, you can set up parallel circuit, series circuit, to model the flow of anything. There are naturally resistive quantities, and the amount of flow, that's the current. So we can calculate the resistance of a single capillary vessel. And we can also calculate the resistance of the, maybe the heart, left to the right. Mm-hmm. Yeah. And then we can say that, you know, through analogy of circuitry, we can say that it must be the resistance of a single capillary vessel over the resistance of the entire flow. Okay, convert everything into meters. Right? So let's see how big this number is. So all the numbers gave me 0.72. All the exponents will give me that's 935 -1. Wait a second, that's not right. It's too small. Oh, because that's pi r to the fourth. Yeah. So I need to divide this 4 times. 2.044. And here I would have 24. So 21, 15, 17, 11, another 2, 9. Okay. Yeah, that's a very useful analogy. That's used in a bigger. I think it's in IPHO.
So it's just
Mm-hmm.
the speed of the big one
Mm-hmm.
times that number.
Yeah. So by definition, the flow rate over total cross-sectional area. So yeah, so what's really interesting is that idea that we can model flow all the flow problems this way. Okay, so let's look at the next one. So that charge is by definition a integral of the current, but in this case it's area under the curve, which is 1/2 1000 100 times 1000 times 0.1 times 10 to the negative 3. Excuse me. So that's roughly 5 coulomb. And the average current is by definition the integral of the current over the integral of time. But in this case, it's simply Q over tau. That's the definition of average. $50,000 ampere.
So for the 3.11, you have to use the capacitor.
Yeah. And they they provided the data for the cloud and the total number of lightning striking Earth.
So it's Q times V, right?
Yeah. So the total energy will be N lightning multiplied the energy stored in each lightning. I mean, there's some there's some fancy ways to do this, but I think the easiest way is, yeah, 1/2 QV sounds pretty easy. And that's the total energy. So how long can this sustain all the light bulbs? It will be energy over power. Yeah. Oh, that's for it's asking for everyone, so you also need to divide by the number of person. Number of person. So it's something like this. The total energy over number of people over um, the power of the light bulb. So let's look at this one. This is a thermal problem.
So you just use the Fourier law and you multiply that by the surface area of the spherical egg.
That's right, yeah. So for 3.5, we are given the coagulation temperature, so um, that since everyone needs to get to that temperature, we can just use Cm delta T. We are given the density, and we're also given the radius. We're also given all the temperature. This is joules per Kelvin per gram. So multiply this by 1,000. Density is 10 to the third. Radius is 2.5 centimeters. delta T is 61 degrees, so that should be enough. Okay. So for 3.6, we will be using the Fourier's law because the water is boiling at temperature T1. The center of the egg is 4 degrees Celsius. This is an exponential process, in a sense. You know, if we graph the temperature at the center, it will go from 4 degrees Celsius to 100 degrees Celsius. It's an exponential growth because the rate at which temperature rises diminishes.
As the temperatures get closer to 100.
Exactly, yeah. So this will allow us to say the heat flow is equal to 0.64 times 96 over 2.5 centimeters. Okay, then we can look at this unit. It's joules per second. Joules per second per Kelvin per meter, and that's Kelvin per meter. So this J is joules per second per meter squared. We don't actually need to think too much. It really should just be J times power squared. That's the power. Just by looking at the units, that should be the power. This will give us the joules per second. So in a sense, the previous one is like the power density or intensity of the heat. The intensity of heat going into the egg.
How come you don't choose 4 pi r squared?
Oh yes, I should use 4 pi r squared because it's spherical. Okay.
No, the last one just divide the total energy by
Yep, exactly. Yeah. Joules over joules per second. This is somewhat of an estimation. Um, this may be the characteristic time because the exact problem is a thermal diffusion problem where the exact equation is a partial differential equation because the temperature of the egg is dependent on both radius and time. Th- Does that make sense?
yeah.
Yeah. That's the exact solution. So really, it will take a very long time for the center to reach 100 degrees Celsius. And this solution is an approximation. This is maybe uh, a characteristic time where the temperature reaches temperature at the center um, reaches maybe 100 degrees Celsius minus 4 over E plus 4, something like that. It's not fully heated up yet. Okay, so let's look at the last one. This one um, is an optics problem. Okay, so maybe draw a picture first. Okay. So when we look at something, um, this is basically true for human eyes as well. Human eyes is essentially a camera. So sometimes we cannot tell two things apart. Okay, we cannot tell two things apart, and there are two reasons we cannot tell two things apart. The first reason is due to diffraction of light. Because the human eye has a pupil. That pupil has a certain radius. Okay, and this is a result from diffraction. It's called Fresnel diffraction. When light goes through when paralight goes through a small opening, it will spread out. Okay, it's a common thing for all waves. How much will this spread out? You can measure the spread out by angle. Okay, and the angle is equal to 1.22 wavelengths of the light over the diameter of the aperture. And in fact, we discussed this before. This you can also explain why this happens through quantum uncertainty,
Yeah.
Heisenberg uncertainty. Because you don't really know where the photon goes through the aperture.
So there's the vertical
Which
uncertainty.
results in exactly which results in a um, uncertainty in the transversal direction. So the light moves longitudinally, but due to the aperture, it introduces transversal uncertainty. Okay, so that's one result. The other result is something called Rayleigh criteria from Lord Rayleigh. Rayleigh criteria. This one says the distance between the image the whatever you want to see, the objects, okay, that distance has to be bigger than the wavelength of light. If you have 2 points, um, the distance between these 2 points have to be big enough.
But in
Okay.
reality,
Mm.
like, since the wavelength is so small,
Mm.
is that really the case? Or
Yeah. So in reality, most of the time, this is not a problem because visible light has very small wavelengths. Also, this is the reason why um, we use electron. We use a very powerful microscope based on electron because we need to increase the energy of the electron such that through the Broglie wave equation, the the wave of the electron can be much, much smaller than the wavelength of visible light. By using very powerful electrons, we can increase our ability to see things. In fact, it also helps with the Fresnel diffraction. So let's take a look at that. Let's see some pictures. Okay. Yeah. See that that 1.22. That 1.22 comes from a function, the solution of a function. It's a 0 point. It's a 0 point of this function. Okay. It's just a very specific number. It's really a it's really a solution where the function becomes zero. So that's one effect, okay, due to diffraction. That's the second effect. So the image on the retina, this point and this point, those two images, the distance between those 2 points on the retina, they have to be sufficiently far away. Otherwise, our eyes cannot tell them, cannot tell the difference. Same thing for the for cameras. Okay. In reality, it's very hard to do this due to other optical effects. From 10 kilometers, most people would not be able to see anything because the air is not uniform. And there's turbidity, which makes the air sort of so light. It's essentially refraction of light. Light has to bend bend around, traveling such distances, which changes the angle significantly. So this is really very ideal situation that you can see a car from 10 kilometers. Okay, so I think we can come back and do this. So once we establish that, Um, this distance, the minimum, is the focal length times the separation angle. So if you assume horizontal light comes in, they converge onto this point. And this angle is roughly 1.22 lambda over d. And f over d by definition is f sharp. So the best resolution will be achieved with the smallest f number. In this camera, it will be 2.
Is it 1.22 f sharp times lambda?
Lambda, oh, f over d. Hmm? F over d, yeah, lambda. That's right. F sharp is f over d, so multiplied with lambda. Yeah, that is pretty good. So that's 1000. The necessary, so this is basically a geometry calculation density. It's a square chip. So um, 5 to the 10 to the 6 under the square root. That's how many points in each direction times, um, well, we need to solve for n. So it's the square root of n times delta x equals L. So why does it give us the NP then? Probably smaller 35 times 10 to the third over 1.22 squared. How big is this? So that's much that's much bigger than this one. Oh, but that's okay because that's the that's like that's overperforming. So that's fine. So this camera wouldn't be able to do that. Okay, so I think the rest is relatively easy now. So you want in 3.3 you want delta n sorry square root of n times 1.22 f sharp lambda, which is delta x equals L, right? So you just solve the new f sharp. Human eye has angular resolution phi equal to 2 arc minute. And typical photo printer will print a minimum of 300 dpi. So that's 300, that's delta x, well that's maybe call this delta y. Delta y equals 1 over 300. Mm, that's the angular separation. That's the z value. Yeah, that's the human eye resolution. Bigger than this is, we know this is bigger than 1.22 lambda over d. So theta is delta y over z. Z equals delta y over theta, 1 over 300 inch over 2 arc minute, which is uh, 1 over 60th of a degree. Then converting to readings, 3.14.
They gave it at the bottom of
Oh,
it's 2.91 times 10 to the minus 5.
okay, that's then that'd be easier. Yeah, so I'm curious what this number is. 1 over 300 times 2.54 times 2.01. That's how many meters there is. So 14, 15 centimeters away. That seems reasonable. Yeah. Okay, is that all okay?
Yep.
Very good.